So let's talk about double integrals over regions that may be described by functions of y. Previously we've discussed regions that may be described by functions of x. Okay. So now take a look at this graph here. Something you'll notice is that the purple and blue curves there fail the vertical line test. They are not functions of x, but they pass the horizontal line test. So they are functions of y. You can talk about this purple line as x as a function h of y. So the strategy here then is to fix y first. So that means you integrate y second. So the second variable is fixed, so fix y to some value there between c and d, and integrate over x, move along the x-axis from this point here to that point there. Okay, what is that point? Well, it's going to depend on where you chose y. If you chose y up here, it's going to be this point here, right, to that point. But if you chose y over here, it'll be from this point to that point. Generally, it's going to be from g of the y that you chose to h of the y. Okay, and what do we do after? So what would that give us? What's the result of this? That would be the area of a slice of this graph, which you can't see. It would be coming out of the z-axis. It would be the area of the slice at that fixed y. And then when you integrate from y equals c to d, you get the volume. Since you're multiplying by dy, you're multiplying the area of a slice by dy to make it fatter and get a volume of width dy. And now add up all of these slices with small volume, d, from c to d. And it's important that in this integral, gy be less than hy in from c to d, the interval of y you're considering, and that c is less than d. Okay, that will ensure that we get positive areas in our region, and then the volume can be net negative if the graph goes below the xy plane, but the area should stay, the area of the region should stay positive there. So let's take a look at an example. We want to find the volume of the solid below the surface. Okay, it's not plotted here, you can't see it here. It would be coming out of the z-axis, and above the region R. So above the xy plane, above the region R in the xy plane. And what is that region R? It's bounded by the lines y equals x. That's that blue line there. Y equals 8 minus x, that line there. And y equals 1, which is this green line that you see there. Okay? And again, f xy is strictly greater than 0 on R, so we are indeed getting the volume between the xy plane and the graph of the surface. We don't have to worry about the graph of the surface dipping below the xy plane, and hence not defining very well what we mean by the volume between the graph and the xy plane. Okay, that's not to say that you can't get a negative net volume. You can. Okay, it's just if we want the volume between the region and the surface, no, then it should stay above the region, and it does. Okay, so what are we after then? We're after computing this double integral. Okay, and these pass the horizontal line test. Okay, so it's best to describe them as a region with functions of bounded by functions of y. You might say, well, these also pass the vertical line test. Definitely they do, but notice that the top here is bounded by the blue line and the purple here is bound in the, you know, to the right side of this region. You know, the top part is bounded by the purple. Okay, so you'd have to change bounds. And if you insist on integrating over y first, we'll talk about that in a second. But let's carry out this integral in the easiest way, which is moving from the blue to the purple. Okay, and so what do we do when we integrate? So y is fixed. Let's fix y. Throw it somewhere between 1 and 4. Okay, and integrate y from where to where? Well, it's going to depend where you threw your y. You throw your y up here, you're going to integrate from this to that. But if you, for a general y, which we just leave as arbitrary, integrate from here to here, what is that? That's x equals y there. So you're integrating x from x equals y to x equals 8 minus y, which is the purple line, okay? That's given by 8 minus y. You're integrating from the blue to the purple, okay? And this y is to just kind of create a mental image there where y is being fixed, okay? For our first integral. Doing that integration for x, this whole thing is treated as a constant because y is treated as a constant when you integrate over x. So you get that x there, and you know, that's its quote constant coefficient. And plug in the bounds into x, and you get this guy. What is that? That's the area of this slice, you know, of the function, which you can't see. It's coming out of the page. But this would give you the area of that. And now the next thing to do is to integrate y from 1 to 4, okay, to get that whole region. So you take the area, ay, multiply it by dy to make it a volume, a thin slice now. And you add up all those thin slices of volumes from 1 to 4, and that's what this second integral is. And straightforward computation gives you that it's approximately 23.09. And so what you're seeing here is the function that we just computed the double integral for. And we could start at y equals 1 and move along. You could see that that greenish volume is getting bigger as we move from 1 to 4 at the end, and we get the total volume at the end, okay? So that's the function that we're finding the volume between that triangular region and the graph of. Now, what if you insisted on integrating over y first, okay? So that you fix x to some value. How would you carry that out? How would you switch the order of integration? It's not as simple as just moving these two integral signs, switching their order, and switching the order of these differentials. Absolutely not, okay? You have to open your eyes when you want to switch the order of integration for functions of general for regions for general regions, okay? And so here is actually how you would do this. So notice that if we want to bound this as functions of x, well, we're going to need to use two different functions of x depending on where we are along the x-axis. So if we're between 1 and 4, the top bound is going to be this blue line, y equals x, okay? And that's what you're seeing here. Okay, so this is the integral as we're doing it over this pink region there. Okay, so we do that, the integral over the pink region from 1 to 4, from 1 to 4. And what do we do from 1 to 4? We fix x, we integrate x from what? From, yes, we fix x, we integrate y from y equals 1, right? The function y equals 1 to the function y equals x up here. Then we could do this integral from 4 to 7. That's what you see here, from 4 to 7, from the function y equals 1 to the function y equals 8 minus x. Okay, that's what you see there, from 1 to 8 minus x, and that's going from 4 to 7. That's how you would switch the order of integration if you just insisted on integrating over y first instead of x. You could see that it's just simpler to have done it with x first.